As you're about to see, example 7 gives us yet another complication that occurs whenever we do sometimes integration by parts. All right. In this example, we've got the antiderivative of e to the x sine x with respect to x, and notice that we really have we have two transcendental functions, two super irrational functions in e to the x sine x. So you might think, well can we use the that tic-tac-toe method that we just discussed in the previous video? Well, here, let's take a look. Remember that with this tic-tac-toe tabular method, whatever it is that you choose for u, its derivatives have to go down to 0. They have to ultimately disappear. So let's say, for example, we chose e to the x to be our u. Well, the derivative of e to the x is e to the x all day long, forever. So it's never going to go down to 0. Okay, so what about sine x? You take its derivative, it's cosine. You take its derivative, it's negative sine, and then so on. It just cycles back and forth on itself. So neither one of these two things would go down to 0. That's a problem. So we can't use that tic-tac-toe tabular method. So let's just go back to using the traditional integration by parts, starting with limit. So we have e to the x, and e to the x is an exponential function. And then we have sine x, and sine x is a trig function. So the sine x is going to be our dv, meaning that e to the x is equal to u. We'll take its derivative, du is equal to e to the x dx, and notice that it did not get simpler. That's what we want to happen, but it did not get simpler. As a matter of fact, it stayed exactly the same. Okay, so then dv is equal to sine x dx. Take its antiderivative, v is equal to negative cosine x plus c. All right, now we're ready to rewrite in terms of integration by parts. I'm going to go ahead and write our integral down again. E to the x sine x dx is equal to uv, bring the negative sign right out front, negative e to the x cosine x minus the integral of v du. And there's already a negative there, so it'll cancel out with a negative on the outside, e to the x cosine x dx. So notice that we exchanged e to the x sine x for e to the x cosine x, which is no less simple than we started, which is an issue. This is the complicated part of this. All right. So let's say it seems like what we're going to have to do is integration by parts one more time. And hopefully that resolves the whole thing. Let's see. Well, we still have the exact same setup for our u and our dv because we have an e to the x exponential and cosine x being trigonometric. So u is equal to e to the x, du is equal to e to the x dx. Looks familiar. dv is equal to cosine x dx, and v is equal to a positive sine x. All right, copy everything down. Just go with it. I know it seems like a lot to write down, but just go with it. Let's write it all down. E to the x sine x is equal to negative e to the x cosine x. And now our new uv, maybe I put brackets around this, I don't know. Maybe it's needed, maybe it's not. uv is e to the x sine x minus the integral v du, which is e to the x sine x dx. Were the brackets needed? In this case, they definitely were not. Okay, maybe if we had to distribute something through that, or we had factored out a number or something, but we didn't, so we didn't need the brackets. Wait a minute, look at our new integral. Our new integral is e to the x sine x, which is exactly the same thing that we started with. So notice that it just cycled back on itself again, which for us is very beneficial because we can solve for it. We can take this integral of e to the x dx, or sine x dx, and we can just add it to the other side, and we would have two of them. You probably think, well, how does that help me? Let's see. We have 2e to the x sine x dx is equal to negative e to the x cosine x plus e to the x sine x. And notice that there's no more integral over here. It's all gone because we added it to the other side. And if I wanted to solve for the original antiderivative of e to the x sine x with respect to x, all I have to do is divide by 2. Crazy, right? All right, instead of divide by 2, I'll just multiply by half, which is going to make our answer antiderivative e to the x sine x dx is equal to negative 1/2 e to the x cosine x plus another half e to the x sine x. And it's at this point that we should put our plus c. So here is the insane thing that happens with some of these things, especially when you have a transcendental times a transcendental, that it will eventually cycle back to the original antiderivative, which you just bring back to the other side of the equation and you solve for it. Right, this one just had 2, but it's possible it could have 3 or 4 of them that it eventually cycles through in order to get back to the original one. Okay, so just to demonstrate that this actually is valid, let's find the derivative of this guy. Right, so we'll have to use, looks like the product rule a couple of times here. And when I do, I'm just going to take the negative e to the x as being our first function. Or I can bring the halves out, it doesn't matter. All right, so the derivative of negative 1/2 e to the x is negative 1/2 e to the x times the second function cosine x plus the first function negative e to the x, so it's going to be minus negative e to the, no, e to the, come on, times the derivative of cosine, which is negative sine, I'm just going to cancel out with this one here. Okay. Plus, now treating a half e to the x as our first function again, 1/2 e to the x times the second one. We've got sine x. All right, and then plus 1/2 e to the x, the first function, times the derivative of the second function. Derivative of sine is cosine x. Derivative of c is a 0, and then you can see, as we expect to happen, these two cancel out, and then I have a half of, and another half, which makes a whole, e to the x sine x, which is what we originally started with.